Okay, hello everybody. Thanks for attending the talk. I'm Zhen Dong from National University of Singapore. Today I'm gonna present our recent work, time travel testing of Android apps. This is a joint work with Professor Marcel Bimo from Monash University and Lucia Kojukoro and Professor Abik from National University of Singapore. So today, mobile apps are everywhere. We use mobile apps almost in every aspect of our daily lives, like food, traveling, shopping, communication, education, and so on. So mobile app testing becomes very important to make sure the app we are using works correctly without crashes and hanging or something like that. And the idea of mobile app testing is to generate a series of input sequences and feed them to the app and test. If the app works correctly or incorrectly, then the bug is reported. Until now, there's so many techniques has been developed, and a lot of them achieve the promising result. However, most of these techniques focus on input sequence generation. For instance, search-based techniques, they start execution with a bunch of random generate input sequence, and then mutate them with the hope triggering new program behavior, and eventually trying to achieve more code coverage or finding more bugs. Unfortunately, these techniques face a challenge to find bugs in deep states. These techniques often generate a lot of input that reach easy-to-reach areas, but few input that reach deep states. So let me illustrate with a map of a popular game, Super Metroid. So probably most of the generated input reach area around entry, and less input reach the middle area, and the rare input reaches area at the end. So this leads to a phenomenon that easy to reach area are intensively explored, but deep state are not explored adequately and leave bugs in deep state uncovered. And several techniques like search-based testing techniques address this challenge by performing a selection over the input sequence. They select the input sequence that trigger new program behavior and for mutation, and hoping to generate the input sequence that trigger more program behavior. But this kind of input sequence selection for hitting deep state can be insufficient. Suppose this is the input sequence that leads to a deep state, and this input sequence is selected for mutation. However, they don't know which part of the selected input sequence touch the deep state and trigger new program behavior, especially when the input sequence is very long and, for example, more than one type of input in the sequence. Then the part of the input sequence that leads to deep state can be broken during the mutation. Now, this results in that the generated input sequence cannot reach deep state again. So this kind of a selection strategy might be insufficient for hitting deep state more often. So to address this challenge, we propose a time travel testing idea, where we directly save program states instead of saving input sequence. So during execution, we observe each visit state and save states that are interesting. I mean, interesting means here a state has potential to trigger new program behavior. For example, the state that has never visited before. And when the progress is slow, for instance, the execution keeps looping among certain states, then we terminate the current execution and restore the most interesting state that previous is saved and launch a new execution. And in such a way, the new program behavior can be kept explored. And the deep state can be identified and saved during execution, and can be systematically explored by restoring them. So the bugs in deep state can be found. So this is the idea. And our time travel idea is designed to enhance existing techniques. As we see, our technique mainly consistent of 3 components: an interesting state detection, a lack of progress detection, and progressive state selection. An interesting state detection component checks whether a state is interesting using code coverage or state information collected during execution. And progressive detection component monitors recent visited states and check whether the progress is slow. For instance, execution falling into a state loop. And a state selection component maintains program state and select the most interesting state when time travel is needed. And our framework is highly configurable. The strategy, such as how to identify interesting state, can be configured by users. We implement our idea, time travel idea, into Android Monkey and call the tool Time Machine. To achieve the high efficiency, we identify a program state on Android side and maintain the program state on desktop set. So more importantly, we put the whole framework into a Docker container such that we can easily launch many containers for parallel execution. Okay, let us go to evaluation. In the evaluation, we answer 3 research questions. First, how effective is the time travel strategy? The second, how does the time machine performs compared to state of art? The third, how does time machine performs on industry apps? Okay, for the RQ1, as we see, the time machine achieves a significant improvement over the baseline tool Monkey in both code coverage and the number of founded crashes. So this means the time travel strategy is effective on finding more crash and achieving more code coverage. And for RQ2, we compare the time machine with Sapiens and Stoat, which are 2 recent Android app testing tools. And the result shows that time machine achieves the best performance in both code coverage and number of founded crashes. And for RQ3, as we see, time machine also achieves the best performance on industry apps. Yeah, this is the evaluation. Okay, let me conclude here. Our research shows that saving and restoring states goes a long way towards a more systematic exploration of the state space. And our time travel framework is publicly available and can be used to enhance existing techniques, such as random testing and search-based testing tools. Okay, welcome to use it. Thank you.